Good morning, everyone. Today I'm going to explain about the project which I have done with the help of Emerxte team as a part of internship. Today my project name is real-time EV dashboard and ADAS warning system. This is the type of system where it is created, which has an ADAS. It is a EV telemetry system. This is a dashboard which shows the data of speed, SOC, motor temperature, torque, and with ADAS driver safety metrics. ADAS means the bird view complex. It shows how it uses sensors of HCR, H04 sensors to track the distance between front vehicles, right vehicles, and left vehicles, and it shows into the dashboard to enlight the driver. And we also added the TTC's proximities blind spots with the use of STM32 and UART protocols. The first thing we used for this is we created all the code in STM32, and we used first of all we used the tools like STM32, PiximLab, and Teraterm, and Python dashboard. We first coded all the code in STM32 and fixed it to the PiximLab, and the readings were delivered to the Python dashboard, which is later coded in VS Studio. The UART protocol, the UART transmission link we used is 115200. That is, a Python receiver is non-blocking with a ring buffer. And the STM32 build will collect the sensor and ADAS data in the real time. The real-time telemetry is same. Speed it sampled at 2050 Hz, smooth with IR filter and MCU timestamp. And the state of charge, it is computed in coulombs, as we know, and it is transmitted as percentage 0.1% resolution. The motor temperature and the torque are displayed in the dashboard. ADAS logic and safety features. We used TTC, which is time to collision. The formula for TTC is distance by closing velocity. When closing velocity is greater than 0, it uses exponential smoothing to prevent fast triggers from noisy events. And proximity zone, and we also added the system called blind spot detection. And the data framing and all things. We used firmware emits ASCII frames and read quality debugging frames. For example, let me show you the code. This is the workplace where we have worked and created all this magic. And the first we created it started with the blinking of LED, which here is the main. In main we included so many header files which are useful, that is include main.h. These are all basics, and the common.h where the real project started, and the main thing is started with the evcontrol.h, and evcontrol.h has it has given the many parameters like acceleration pedal, brake pedal, speed kilometer, motor temperature, SOC, power in kilometer, range in kilometer, and driver mode and state. All these are initialized and used in evcontrol.c. As we see here in evcontrol.c, v is equal to ev, SOC is equal to 100, and the driver mode is normal, and motor temperature is 25. As we know here, acceleration pedal is also with acceleration pedal. We used potentiometers for acceleration pedal, brake pedal, motor temperature to simulate the real-time world. And here in EV update, we update the state of the vehicle. If we have switch cases for the state of the vehicle, EV state, this case state parked, if EV motor torque is 0 and result level is 0. If acceleration pedal is greater than the readings of the readings that are available, the state is equal to state ready. And the state ready, the different types of states are state ready, state parked, state ready, state driving, state region, and state fault. All these are covered in a controlled .c and control.h files. And the next one we move to, that is ADAS.h and ADAS.c. In ADAS.h, that is, in here we included the bird view, that is the front, left, right, time to collision, collision warning, blind spot left, blind spot right, over speeding, parking, active and parking score, around priority. In this we have we have used HCRS04 sensors to track the data from the, as we know, HCRS04 sensor is a sensor which tracks the data by sending the signals and receiving the signals. By that, by the time of receiving back the signals which it has sent, it calculates the distance of the object which is away from it. And we have used it in the ADAS.h. In ADAS.c we have initialized all these. In ADAS.front centimeters and left, right, and to collision, all these were mentioned in it, and these are all mainly here. Wait a minute. They are updated here. The ADAS is updated here, and the all are initiated here by.c to show in the configuration. In the next we went to the timers, and the timers we used is timer 1 and timer 3 for the basics basic blind spots, and timer 2 for the counter. And as we know, here we initiated the ADAS and we initiate the EV init and HCL04 init sensors. And here the timers are used for this for blind spots and this for counters. And next one we used is fault. We move to fault.h and fault.c. The fault.h and fault.c is containing many types of functions which it shows what type of fault it is. That is, it has 4 types of fault, that is 00, 01, 02, 04. 01 is for motor or temperature, 02 is for battery criticality and low, and 04 is collision critical. As you know, for fault.c we have initiated all this, and it takes the EV motor temperature, SOC collision warning, flags, and all these, and it gives the faults about what is the problem with the vehicle, and we can come to know what is the problem by seeing this. And after that we have moved to the ultrasonic.h. I forgot to tell what it is with fault.h. We have ultrasonic center, which is a HCSL for in front, left, right, and counting 3. And here in ultrasonic in ultrasonic.c we initiated all these. If here we retrieve the HCSL for in initialization function, we initialization it here, and all this happen here. And the next we move to the UART shell, UART shell.h, which is type it gives data from the PyXimLab to the Python dashboard. It is like a bridge which connects between both the Python dashboard and PyXimLab. And in here, when we come back to the main.c, we can see these are the variables we have given, and these are the static voids we have given, and these are initialization class surfaces. So EV update every 10 minutes via timer 1. Having a given timer 1, flag is equal to event, flag is equal to 0, EV read.ec, that is dt is equal to 10 milliseconds. For every 10 milliseconds, our data will be regenerated. And if for printing all this, we used process like if sensor. Let me wait, I will show you that. For printing all this into in virtual terminal, we use the function print status, which is a data type. That's a data picture function which connects with this static data type, and all this work with is it prints speed, it prints SOC, it prints motor temperature, it prints torque, it prints axle It prints a brake pedal, range kilometer, time to collision, front distance, left distance, and right distance. All this in Python dashboard. So after all this, we built this file. That is, we built this project, which is given as a we have created the binary file, and after that we'll move to the PixelLab. After uploading the PixelLab, going to the PixelLab and going to the spare parts, here is the terminal. We are seeing these are potentiometers, which is an acceleration pedal. This is a brake pedal. This is for seeing this motion pressure, and this is for front. This is for left, and this is for right. This is virtual terminal, and these are alarms. By giving this thing, wait a minute. See, we can see the data is printing here, and if we as we decreases this, the buzzer should on, and the buzzers are on. This is the potential, the acceleration pedal. We decrease and we can increase this. This is first in this motor temperature, and all these are connected with the basic things, unlike this. And this is the virtual serial ports. This is the serial ports where we registered with COM1 and COM4. It is running on COM1, and the PixelLab is connected with COM4. As we can see here, it is connected with COM4, and 115200 with the UART serial number is connected to COM4, and this is connecting. This is acting like a bridge between COM4 and COM1. As a result of COM4 and COM1, as we see, we have selected this here, and it is generating various things. And after that, by knowing by knowing the command prompt, by opening the command prompt, we initialized the Python dashboard using all these things. As we see, we have, after going to all these, we can go, that is Python. After entering this command, we can easily access that Python dashboard. Now I will show you the Python dashboard, which is the main thing of this project. And after that, see, this is Python dashboard. As we see, the alarm is critical, and it is showing, since it is critical, because as we see here, we decreased it to 46. That's why here it is showing alarm critical, and the red sign is showing. As we see, the torque is 0, acceleration is 100%, brake is 0, water temperature is 37, alarm is critical, and fault is 004. As we see, fault is 004. For here, if we go to fault.c, fault will be 004, fault.h 004 for fault collision. So collision is happening here. As we see here, the collision is happening. If we increase the distance, the alarm should turn off. As we see, the alarm has turned off, and if you open the dashboard, and it is no, alarm is none. And the distance, this is the right front turn, this is the right car, this is the left car, and this is our vehicle, and this is the speed, and we can increase or decrease the speed. We can increase and decrease the speed. When I will decrease the acceleration and increase the brake, and I will show you the change here. As we see, the brake is 71%, the acceleration is decreased to 47%. This will update in a matter of minutes, and the battery percentage, as we see, 71.5%, and the distance to be traveled is 2,383 kilometers. And this is the ADAS bird view. This is the ADAS bird view, and we can see here the time to collision is 99.9 seconds. Speed is 14 km/h. This is the Python dashboard we are working, which is connected to Blue Pill. This is working on COM1, and the PixelLab, the STM32 is working on COM4. So we have, as we can say, that the PixelLab is working on in PixelLab the STM32, the microcontroller we are using is STM32F103C8T6 and which is 31.25 MPs and 8 IOs. I will show you the wait a minute. I will show you that io.ioc file. It will take some time. Wait a minute. The IOC file in where all the pin connections have been done. This is the pin connections we have learned in this internship. All these pin connections, this for input, output, and GPIO input. This is timer. This is for timers. This is for UART, and this is for ADAS. And the clock configurations have been set into these 9, and here it is enabled to CSS, and it is 72 megahertz max, and this is given by APP1 prescale is divided by 2. All these are configurations that are performed here. By that we can say this is the total project which I have worked for 1 month, and I would like to thank the team of Emerxte and my mentor Jayalakshmi ma'am, who worked really hard to teach us what EV dashboard really looks like, and about the coding, about the hardware or something, everything. So I would like personally to thank my mentor Jayalakshmi ma'am, and team of Emerxte to giving me such an opportunity, and thank you for this opportunity.